There, we are recording. Welcome to the evening of Python coding. This is a meetup, though each time we show some Python tool or library or something related to Python that everyone needs to know about that is useful. Today, we're showing some sort of favorite of mine in a sense, Coiled. I have a history with the people who develop it. In a sense, I know them, so this is kind of interesting for me. And Matthew Zamora is gonna show us Coiled. Matthew is part of the community. He doesn't work in Coiled, so but he's gonna show it, and hopefully you'll be interested. It's basically a library to handle big data and parallelization. Matthew, you explained much better than me, probably.
We'll find out. Thank you so much, Jacob. So yeah, as Jacob was mentioning, the purpose of Coiled is to help with running your data at scale on the cloud. And when we talk about at scale, I'm talking about multiple servers and just making that really easy. You know, we all have to deal with parallelized pipelines at some point in our big data careers, at least. And there's a couple considerations. First of all, Coiled is a Python library, but it's also a company. It's a Dask company, has the Coiled brand. Now, I might butcher some of this. We have with us on the line Sarah, who works at Coiled. We're very lucky to have you join us. So Sarah, feel free to speak up and correct me. Again, I'm just volunteer and such, but thank you so much for joining us, Sarah, and feel free to mute yourself anytime. Okay, so when we are working with Python, you know, we have these large data sets, there are quite a few considerations. Sometimes we reach practical limitations. You're literally, your laptop or your desktop just won't fit the data, or it's going to take an irrationally long amount of time to process through something. Now, you could set up a large cloud cluster the traditional way. You know, obviously, AWS came in and changed the game as far as what you can do with spinning up servers, and we're leveraging that fact. But you know, it used to be, for example, you would register for a large server, and you would get access to the SSH, and you'd do all the manual configuration, and you know, it was quite a few steps to get to the point where now you're running some kind of large data set. What I will say is that what essentially, in a nutshell, Coiled is going to let you do is it's going to let you spin up and spin down your server resources very quickly. So it uses it for just as long as you're processing, turns it off after, and it's going to be a very efficient way to cost control your project. So to give you guys a little allegory for why this is important, in some of the prior work that I was doing with the computational bio research that we were doing, I had a group member who was saying, hey, for this data set, can I run this really large algorithm? It was Bayesian analysis. I don't really know what it was. It was kind of doing a kind of a fitting algorithm, and it created thousands and thousands of files, and it was massive. And he said, I can't run this on my local. Can you get me a server resource? So this was before my exposure to Coiled, and I said, sure, I'm just going to, you know, pay for it myself out of pocket, and I'll get you these large servers. So I got the large server. I turned it on. I'm getting billed for it all this time. You know, 4 days of me getting billed for it to hand it over to him. He does his processing over the course of a week, and then 3 weeks later, after he's done, I remember to go back and turn it off. So suffice it to say, it was about $1,000 for one workflow, and it wasn't particularly fast, and it was very expensive. And of course, me being human, I forgot to turn it off, and I'm not the only one in the world who forgets to turn off cloud resources. So that was a real world, you know, kind of pain point for me. That you know, this was really silly. It was really hard to get the one server up, and it was very expensive, considering, you know, what we ended up getting out of it. So that's kind of the primer for why Coiled. Let me go ahead and jump us over to a little bit of a preview. So first of all, more background. You would use a number of uh, uh, possible cloud environments for Coiled. So they support at this time, I believe, Google Cloud, Azure, and AWS. So you can just pick one. They definitely have different cost structures. There's a little bit of nuance. From my perspective, it did. I just picked one that I prefer. I wasn't dominated by cost in this decision. But you pick a cloud provider, and they're pretty agnostic. The Coiled platform's pretty agnostic. One of the things you do is you log in, and you have to kind of associate your account with a cloud provider. So here's my cloud provider. It's a connection essentially to the Google environment. This is a one-time setup thing. So once it's set up, your life's easy. It is a pain point to have to set this up the first time. It's not a huge one though. It's a lot less of a pain point than actually going into Google Compute and actually figuring out how to set up all your servers. They make it pretty straightforward, but it is something that you have to do and you have to set up. And at least if you can get to the point you're running your demo project, then you're in pretty good shape. So they're going to, I believe at this time, and Sarah, correct me if I'm wrong, but it's something like the billing starts if it's over 100,000, or sorry, 10,000 compute minutes. Is it something like that, Sarah?
Yeah, that's exactly it, Matthew. It's 10,000 CPU hours, which is a little bit a metric that doesn't always make sense to folks, but it's a really pretty generous free tier that lets people do quite a bit of computation before paying anything. But I'm sure you'll mention how much you used up in your demo and give people a sense of that.
Absolutely. It's fair to say, I'll reinforce that Sarah's saying it's pretty generous. 10,000's a lot, given that you run it just for as long as you need it and you're turning it off right after. So it's very efficient. So after you have your cloud platform of choice, one of the keys here, like where does the billing come in? You do have to give like an open-ended credit card to Google or to Azure or AWS. So keep in mind that these are still real-world costs, and you still are getting billed. There's no true free lunch, but you are. It's very reasonable, and we'll kind of go through some of the costs coming up when we're running this. But you do essentially give them a credit card so that they can assign a certain number of servers. Do keep in mind that if you just opened your account, you're limited to a finite number of servers. I can't remember exactly. I think it's something like, for me, it was like 64 servers or 32 servers. I think you can get to like the thousands of servers. You have to kind of apply for it though. It's not out of the box, at least not for the account that I created. So let's go ahead and take a look now, without further ado, at some of the code. So first of all, import Coiled. There is a pip for Coiled, which is super easy, super lovely. And it's really kind of a dirt simple premise. We're going to set up a cluster right here, right in this one line. And we're setting up this coiled.cluster, and this is the magical number, number of workers. This is going to be the number of servers involved. Everything else is just kind of config relative to that. I'm just giving it a name. I'm saying a region. Now, depending, there's a little bit of art to what region you pick. First of all, there's speed relative to you. Perhaps more importantly is the speed relative to where your data is. Some regions, if your data is very large, you're going to want your compute co-located somewhere near that as well. You're going to end up saving money if they're closer. That's kind of just a rule of thumb. Ultimately, of course, just a personal preference wherever you want it, and you're getting a cluster set up. I'm going to take a segue to talk about our data to put kind of our goal into context. So there exists a data set that's very large called ArchiveX. Archive. And what it is, it's a service that collects pretty much all of the scientific publications and kind of
It's a
documents.
reference server. It's
Yeah,
where scientific publications go before journals pick them. But not all of them. There are several preprint servers like this. Archive is one of them. There's bioarchive, there's Research Square, there's medRxiv. Then there are others. I don't even remember.
That's right. This is not exhaustive of all of the world's publications, but they have a surprisingly large collection, many hundreds of thousands.
Many good papers are there and not even appear in journals. So yes, it's good. Sorry, Matthew.
No worries. Yeah, so the point is that this is a very rich data set. It is human knowledge, it's PDFs, and it's science, right? These are really rigorous articles. We want to play with it, right? We want access to that. And you know, they being so kind, they do give you these access. This is sponsored by Cornell. And there's a few ways to access it. The one that they kind of point you towards if you read their documentation is this AWS. So there is an S3 bucket. S3 is a storage container on Amazon, and it just specializes in data. Like they store data for long-term archiving. There is something equivalent that we're actually going to use, which is there is a Google equivalent of that, which is a Google. Let me see if it's this format right here, Google Storage. Yeah, there's a Google Storage bucket that also has this large ArchiveX data. So how do they store this? Well, there's going to be over 5,000 tar files, which are archives, zip archives, and each tar file might have 20 or 2,000 PDFs in it. So it's just a very, very large data set. Nothing I would ever want on my computer, and certainly nothing I'd want to process sequentially if we were doing any kind of analysis on it. So we have this very clear data set that, in a sense, is obviously parallelizable. The kind of this concept of parallelization, you have to ask the question, what is the most atomic part? Can that atomic part be put in parallel, or does it have to be sequential? In this case, the kinds of algorithms we're going to do are parallel. We're going to search for things in those PDFs across all of them in parallel. So let's continue then just with kind of the basic guts of Coiled. So we've setting up a server. We're declaring how many that we want. Now, what it's going to come down to is we're going to do arbitrary Python and be able to run that arbitrary Python across each of the instances of that server and these workers, if we want to use that term. So what it comes down to is there's going to be for this cluster, we're getting a client to it, and then we're just client.submitting something. We're submitting a function in this case. It's kind of like a map function, if you're familiar with that concept. You're taking a version of it and you're kind of sending it out. So what this is going to do is it's going to run the function called increment, and we're going to take an input of 10 into the increment function and send it out to the cluster. Just it doesn't really, in this case, is a very, very simple example. Just want to kind of show you the basic premise. So what we're going to do.
Slow down.
Okay.
You're showing it to the cluster. What is it going to increment?
So a value. So
you're giving 10 and you ask it to increment by 1.
Yes.
And you're submitting only this function once, correct?
Yes.
Okay.
Yeah. The point here is just to show arbitrary execution on the cluster. This is also kept really simple so that if you're doing first-time setup, you're making sure that you have access. There are some notes that I have in my other file, but basically there is one-time setup for your system generally, there might be something like a Google application credential, which is like your secret file that logs you into your Google cluster account. And you're going to want to set that up somewhere. There's very clear instructions on how to do stuff like that. But it is like the very first time you run something, just run something very small, just to make sure that you can connect to your cluster and spin things up and down. In my case, I have a file called application default credentials.json, has my secrets in it. And again, that's in part of the spin up documentation. So we're going to just run something really quick. Now, this is something that I'm going to run in Anaconda. So I do have this in the README. Actually, let me take a minute to post the GitHub link, just if folks, for whatever reason, want to follow along. Put that in the chat right here. What we're going to do is essentially these steps. I've already done the git clone, but I am going to open an Anaconda and then activate a virtual environment. So here's my Anaconda. I already have it installed. I'm already in the right folder. And I'm going to do activate the virtual environment. So for those unfamiliar with Python, when you pip install something, or you get these libraries, you can either install them for the whole system, like your entire thing, or you can do it inside of a virtual environment. And what the virtual environment is going to do is it's going to let you have kind of an empty Python instance where you can kind of add dependencies that don't interfere with anything else on the system. So, you know, a lot of times you're going to avoid conflicts if you have two projects you're working on with different versions of a library. Something like this would take care of that because they're isolated. But to use that environment that you're setting up, you have to do this activate step. So now we have this activated environment, and we'll go ahead and run the first Python, which was just that increment function. And we'll see a number of really cool things. So fetching latest packages, scanning. So what Coiled is doing at this point is it's doing an assessment of your local environment. You obviously have a Python that you're executing. That Python itself has dependencies, libraries, everything that's on your a file, your imports. Now, those dependencies, every server that is going to use your code essentially needs those sets of dependencies as well. So what it's going to do is it's going to collect those dependencies, or catalog them at least, and make sure that every instance of the worker server has access to those resources. Let me do. Woda. Hold on a second. What's going on?
Yeah, it may need a sec.
Let me reload. Let me also take a look at my Google Platform Cloud. So one of the things that you have in your Google Cloud account is you set up these projects. So you can have independent projects. The independent projects will have independent billing. This is when you have that secrets file, that's all set up for you. So let's just double check here. Billing, okay. I'm just gonna take a quick look at this one more time. One of the cool things is you can see, you should be able to see the instances in both Coiled and in the Google Compute Cloud. console. So let's take a look. There's actually a past run that we can take a look at here. This is the one that had previously errored out with the name that we had assigned it. So it's saying I'm having a quota issue. I'm going to go ahead and just click on that to see what's going on here. If I might have hit some bad luck where I had run this right before, and but let me see if I can switch this real quick.
Matthew, I'm wondering if you have access to another region in this Google Cloud account.
Okay, I see what you're saying. So I have this. I have not tried another region. We could try another region. Do you know if I have to set that up in Google Compute first, or can I just enter it directly in the coiled?
So let's see, on the GCP side.
So I'm going to go.
I'm not sure what you get automatically, but it seems worth, yeah, giving it a shot.
I'm going to see if I change from east to west just to see what happens. Let's give that a quick try. Okay, give me a second for a little hot coding. Right, there we go. All right, so there we go. Good call out on that, Sarah. What I had seen quickly browsing was that I did hit a threshold on my Google account side where I reached all of the CPU time that I had access to. I just had to go back. I'll do it after the call and kind of set up some more threshold budget for that. But in any case, here we are. We've run. We're getting a result back. So this result is coming here. This is going to be essentially a promise that's returned. So when you work with the any kind of parallel processing, there's this concept of once things are parallelized, you kind of lose track of when something's going to complete because it's not sequential. You're not in control of when something completes. But generally, there's going to be a mechanism in the parallel processing where you make sure that everything that was intended to process has processed, and you kind of reach a merge back point. And that's the premise of a promise in a future. You're going to get the result back at this point, and then we just go ahead and print it. And that's this result we found was number 11. So that's a very simple example. Just let me actually run that one more time, and then we'll take a quick look at the more interesting Google environment. If we can go up to our cloud project and then our compute. So these, hold on. Oh, it's already over. Goes really quickly. Let me run it one more time. This might be a little bit too slow, but you can actually see the resources coming on live as it's kind of doing its thing. I think this is just going way too quickly, but you can see all of the server resources that are assigned, and take a look at them. There's also in the coiled environment, you can see these runs. So this is the current thing that was the current group that is running right here. So that's going to kind of spin up and spin down. So this will I think spin down pretty soon coming up. So let me switch over to the other more advanced example, which is actually doing something now. So now we're going to go back to that ArchiveX data set, this very large data set, and we're going to start to also introduce the concept of cloud storage, because this is commonly how you're going to work with big data. It's either going to be on an AWS S3 bucket or some other bucket. It's not the only thing. You can also use traditional FTP. Anything that's web accessible, there's a way to make it work. But this is, for example, a very common representative big data scenario. What we're going to do is we are going to get from the bucket a list of all of the available files. And so this is the list files command for the ArchiveX data set. So this is the URI, which universal resource index, something like that. It's kind of like a URL, but in this case, instead of HTTP, it's GS. It serves the same purpose though. It's a location for a resource. And we're saying this is the structure of the location of the resource. You have a bucket name and then a path inside the bucket, a file path inside the bucket. So what we're going to do is we're going to pass the location of the ArchiveX data into that format, and we're just going to use a different library. I'm not going to get into too much, but there's a Python library for working with Google Cloud Storage, and we're just going to connect to the bucket and list the blobs. The blobs are the files, and then we're going to build a list. This is building a list right here for all of the files. Get the file name and turn it into your file list. So it's a little bit of a discovery process. You know, all we have to begin with is the path to the resource, and then we're going to do a little bit of discovery inside of it. Now we're going to do another kind of iteration where we're going to iterate through that list, and we're going to get all the file names that end with PDF. So there might be some other metadata there, some junk data. The only ones we really care about are these PDFs. And then here we're printing the first 10 of them. All right, so we'll come back to this. So now we're just going to run, we're going to define an extract function. We're going to run it manually once, like this line right here is like us running it ourselves. And I think what we're doing is so at this point, what we have is we have the files, it's a path, right? This is the name of the file that we know must exist. It's a string. It's not the data itself. It's just a pointer to it. And then this is actually getting that data. So out of our extract function, there comes a place where we're actually extracting the actual PDF as download as bytes here from that Google Cloud Storage resource. And we're just kind of iterating over the file set and extracting them. We're doing a quick check right here, which is we're looking for a string. We're saying, does this string exist in the PDF? What we're looking for is the string matplotlib. It's part of an example that comes from the coiled reference documentation, but it's just checking which PDFs make reference to this Python library. Just, you know, we just want to know. We're curious. What are they using matplotlib? It's basically the question. So I'm going to just kind of go down. There's a little bit of stuff here I do with chunking. So the concept here with chunking for me was that I knew I was going to set up a finite number of cluster resources, and how was I going to break that data set into my cluster resources? So I'm going to end up with these 5 workers. Which workers are getting what? So I chose to kind of do that a little bit manually. I wanted to do a process for chunking the data, and so that's, however you want to allocate. You have some control over that. So now we're getting to the part where we're setting up the cluster. I'm going to go ahead and magically switch this over to the west so that we look cool later. This is again very familiar, right? The cluster. The good thing with the coiled here is that it's not changing very much from our perspective. We're just setting up the cluster. We're getting the client to it. Now we are introducing another library that goes really well with coiled, which is Dask. Dask you don't have to use with coiled, but Dask is really good at distributed processing. So whereas coiled is really emphasizing spinning up server resources very efficiently, Dask is really about managing the distribution of work across resources and being able to kind of do the actual parallelization. So what we get out of that, we're getting from this Dask, we're getting a client, and what the client is giving us is this map function. So the map function is really the heart of what Dask is introducing here. It's the ability to use the Dask distributed infrastructure to do something that is mappable. And so you're passing the name of a function, which is our good old friend, the extract function. And then we're passing it a structure that can distribute into that function. So our chunked list is an input into our extract. And Dask is going to take care of doing the load balancing and doing the delegation to all of the available resources. So again, we don't really have to manage too much of the distribution. We just kind of set a number here, and we just make sure that our functions are able to have this kind of atomic interpretation where it's one method is doing something, and then your data set is able to be in clusters or in chunks or in some kind of way that's going to work with that parallel processing. So we're going to get a set of futures in this case, the plural of what we had before, all those promises. We're going to wait for everything. So go ahead and run it. Go ahead and wait for everything, and then kind of get a status for it. So what I'm going to do is let's go ahead and just run that. All right, so this was the local print, just to give you guys an example of what's in, what I'm saying, there's a path, what is it? Then we get all of the things. We get the number of chunks here. There's 38 chunks that we're getting. And then, apologies for the printing, but I was just printing all of what was inside one of the chunks. And then what we're getting as a result is a true or false, I believe. Does this file have matplotlib in it? So it's just if we look at the return, out is a list, and we're just giving it file name and a Boolean for does it have matplotlib. So we've now run across all of our resources an analysis that does a very quick true false of does this data have this thing. I'm going to show you guys a prettier example. Now, it's not my example. I do include a reference to it in the README, but there is a coil documentation that goes a little bit deeper than this. So I'm going to go ahead and get that one up. So this is kind of the, you could say, the more mature version of what we did. This is using AWS instead of what we were using, which was Google Cloud, but the premise is the same. The question that they're asking is, how popular is Matplotlib? We want to actually go in and, again, all of those, many gigabytes of data, all of those thousands and thousands of PDFs kind of assess that. So what they're going to do is something very conceptually similar. They also have a URI for, in this case, AWS. There's an S3 bucket, but very same concept. There's a file system. They're getting access to it. There's a little bit of logic very similar to us. They have a tar file that they're opening. They're just getting the PDFs in the tar file, and they're just outputting, hey, does Matplotlib exist in this file? So it's very similar to our extract. Everything else is relatively similar. There's a Dask cluster that they're setting up. There's the mapping function. And just kind of skipping ahead, what they're doing by running this is they're getting this graphic, right? So if your question is, how popular has Matplotlib been in publications? Well, this is how popular. The fraction of papers, and keep in mind that this whole thing runs in like a minute. And so this is pretty incredible. Let me give you guys a sense for the billing. You know what we were running. This one, I think, let me reload this real quick. I think that in my first version, so what I'll say is that I think there's something going on with my code where it's not shutting down. I think I need to look at that, but only 23 cents so far. Most of my past runs have been like a penny. Some are like, they look like zero. They're so negligible, the costs. So again, these are the, at this time, this is in reference to the Google Cloud Compute cost. Again, I'm below, currently on this account, I'm below 10,000 for the coiled. So you'd have to look at the billing for if you go beyond that, but I'm nowhere near that on my account, and I'm just paying for the server resources that I'm using. So if you get a sense here also that you're running just what you need, and in fact, these things, there is a stop cluster at the end of the code. So you do, in fact, close your cluster, which is the good sanitation, the good cleanup, and that's going to be generally what's turning off your billing. So again, I think the idea here is that the scenario I gave of working with cloud data, working with buckets, was pretty arbitrary. The point was you can inject arbitrary Python into a set of servers. Those servers are going to get dependencies. Coiled is going to take care of that deployment of the dependencies to all of the servers, make that really easy. The whole thing spins up and spins down in less than a minute. It's pretty quick. And then you're just running your cluster, and you have pretty arbitrary size, of what you actually want to target. So it's very flexible. So what it's going to do, and again, this comes back to how much money I know I've spent wastefully just not turning off server resources. The fact that I can get what I want, and that it's now that I have the one-time setup of having my Google credentials local on my system. Now I can just kind of spin up and spin down large clusters, use it for literally 30 seconds, a minute, 2 minutes, 5 minutes, and just be done. I don't have to bloat my system up. So in any case, that's my introduction. I'm going to drop 2 useful videos to kind of like, if you're interested in supplementing your knowledge. I want to call out that I was inspired by the Bethesda data science talk. They go into a little bit of what I went into, went a little bit deeper. I really got a lot out of that. And then the first video is actually a coiled video, and they're very good at explaining the same project.
Matt, the videos they can actually watch later. Just drop the links in the chat. It's like I want to focus on things that if people have questions, just what they saw so far. Anyone has any questions for Matthew? Come on, you don't know everything. Everyone's quiet. It's the first one always the problem. Okay, I'll ask a question. I'll make it easier for you guys. So you have 2 components here. One of them is coil that sets up the environment. The other one is Dask. Correct? Dask that runs the payload.
Yeah, Dask runs the payload. That's fair to say. And then coiled, sets up the environment. So yeah, that's right.
Someone's asking, what can you use dark mode in Google Cloud? Well, this seems to be unrelated to this, but
I'll take a look while you guys are talking. Yeah.
Lena, you will be able to find a recording on our YouTube channel. I'll post it later. You check out the meetup. You'll find after that. And if you want the evening of Python coding, we usually summarize all the recordings and all the demo code, so you can actually watch later. I'll drop in links later. So this is a question. Any other questions about what you saw? Is everything clear what happened here? Do you have any other questions? And beginners, please do ask. It's also for you. Okay, go ahead.
I have a question. When it comes to the billing on Google Cloud, and the billing through coiled, you still have to pay Google Cloud, right? There's no getting away around that. It's just at a certain point you have to pay also to use the coiled service.
Yeah, that's my understanding. Sarah, do you want to kind of give a little bit of primer on that?
Yeah, sure. Thanks, Matthew. Yeah, Morgan, that's what you said is exactly right. So you always have to pay AWS or GCP or Azure. And then after there's an included amount, which is that 10,000 CPU hours every month that you get for free from coiled. And then if you go past that, then you would start paying coiled a small amount. Okay. I can drop a link to our pricing page too for folks who are curious, but that's basically the goal with the pricing model is to make it so that people who are trying coiled out, seeing if it's a fit, or are part of academic, more research focused projects don't have to pay coiled at all. And then if you're doing more serious production level usage, then you would pay us for that amount.
Okay. And then I was curious about when you look at these billing analytics, do you know what percentage of that bill that we just got, say for 23 cents, was this server spinning up, doing pip install Python and all the dependencies versus actually processing our, I mean, I guess, yeah, especially for the example where we're actually looking for that matplotlib string and all those PDFs, I imagine that was somewhat compute intensive compared to like incrementing +1 and just proving it. I'm just curious in general with these things, how much of the billing is just the server spinning up and warming up and getting ready to go versus actually like running computations on them. And I just wonder if you've discovered any hacks in terms of like saving money with like, you know, once there's a one-time cost of spinning them up, then once they're spun up, you might as well get as much as you can out of them. Just wondering if you have anything to share on that.
I'll take a shot here at this one. So I do think that we have some relevant information here. So yes, the increment demo was trivial, but there was still getting Python on this resource and doing some stuff. And even the one where we had some dependencies, the Google storage and the Dask, it's less than a penny. So what I'll go ahead and say is that dependency and spin up costs are trivial by comparison. Your billing is going to be in your primary I'm doing this loop. So there is non-trivial time that you might have to do. So for example, if your resource has to download data, then you're getting billed to download that data, right? That's kind of not about the spin up necessarily. It's kind of spin up, but it's not strictly the server spin up. It's already offloaded that to your function that's doing the main stuff. So there are some costs to consider with like, well, not only do I have to get to the right part of the loop, but once I'm starting my loop, I have to actually download that chunk of data. That may or may not be trivial, but assuming it's like lightweight data that you're spinning up with, yeah, it's like negligible costs for the spin up.
Morgan, I have something for you to think about. If you're worried about the installation of this pip install, then you don't get why you need that. I'm saying it in a way because the reason you do mass computation like this in parallel is because you have a lot of compute. Like I run disease models and I use Dask for it, and it like takes days or weeks on my local machine. And well, I can get it from weeks to a day or two if I run it on the cloud. So I care less about how much time to install the machine because the payload I actually have to run is huge. If you need those tools only if you really need something really huge or you need something really, really fast and you don't care about the price. You need it fast. So let's put the cost all aside. The thing that might cost you, and this is something you should know, if you are using Dask to actually go and distribute this payload, Dask also moves around the Python libraries while you actually execute it. So there are ways within Dask to actually tell it, or at least in some versions, I don't know what version they are today, maybe things are automated now, but you can tell it, oh, Dask, all of your nodes should know those libraries because you have to distribute all of the libraries between all nodes. And this is something that you should set up. It's not only it has to be pip installed, it has to be like the nodes have to know because basically you start the computation on one node, then distribute it to other nodes, and they all have to be on the same ecosystem. So there are ways to broadcast the libraries before you start within Dask. I forgot the command for this, but you can actually do it in code and say, I need those libraries in all my workers. So this is beyond the coiled thing, as far as I know. Maybe coiled makes it easier. I don't know.
Thanks, Jacob. To add on to your last point there, coiled should automate all of that. So with package sync that Matthew mentioned in his demo, all of that is being handled automatically.
So you don't need to tell Dask, all of your nodes have. You see?
Yeah, but it's a good point that most folks who really find the value in Dask, like you mentioned, are doing like really larger scale computations where things are running for quite a long time. So yeah.
You see, I learned something new. This was something that took me quite a while to understand what's going on. I had problems. Not anymore.
Yeah, you were not the only one. Within the last year or so, that's been a really fun coiled development that we get to share with folks who are using Dask and coiled together. So
perfect. Okay, we learned something new. Any more questions so we can learn something new again? No more questions?
I guess I have one more question if no one else does.
Go
So
ahead.
Google Cloud versus AWS. You've obviously used both, and I was just wondering what made you opt for GCP as opposed to AWS. I know Amazon has a very marketing centric culture revolving around sales, and they've done very well with AWS because of that, and they're a lot bigger than Google Cloud. But I know Google Cloud prides itself on like technical excellence as its main selling point rather than intensive marketing. So maybe I wonder if you found it to be more better or cheaper or just anything you discovered on that.
Morgan, it's a religious question. I'm joking. Go ahead.
No, Jacob's right. This is it's kind of a subjective thing, and a lot of it depends on if you're inheriting an environment. For example, a lot of enterprise uses Microsoft, and therefore they're very biased to Azure. AWS obviously has the longest history. A lot of old projects are like, for example, we saw Cornell is their official support is only for AWS. In my experience, and this is again subjective and other people different, but in my experience, I found Google to have more straightforward billing, to be cheaper than AWS, and to not be as confusing. AWS, I always just get the feeling that I'm getting a little bit nickel and dimed. That's just been my experience. When I have done pricing research, Google has always been competitive for me. And it's just, but it does come down to personal preference. I would say that you can look at the compute pricing. These are all EC2s. And in this example, they're just kind of like the basic standard compute price. So you can do a little bit of pricing research going to each one and seeing for this region, your basic standard compute pricing, what is it? And you can get a more definitive pricing answer. But it's a little bit subjective, and you'll probably be okay no matter what you go with.
Gotcha. Yeah, no, I understand that's a subjective question. I do have one kind of like Python-y question. I think that might be more aligned with what people are interested in here. I noticed at the very end of the file, you actually closed the file handle, the file cluster.close. I wonder, as like a Pythonista, could you use like the with context handler to automatically handle that?
I bet you can. Yeah, I'm sure. Yeah, I think I've seen that. I guess we can do a quick search while we're talking, but
Yeah, like using a with cluster statement and then putting your computation within it. Is that sort of what you're asking about, Morgan? Yeah.
Context
That's a
manager,
pretty common way to use Dask or coiled either.
yeah.
Okay, cool. That's good. That's a Pythonic. That's cool.
Yeah, thank you for raising it. It's something that the beginners here should know about. Any other questions, anyone? If not, we'll close the recording, but stick around. We're not done yet. Any other questions? Questions going once? Questions going twice? Let's see if there's something in the chat. Context managers, someone is asking.
With statement.
Okay. Okay. Questions going 3 times. So before we end, I would like everyone to give a clap. Thank Matthew for his nice presentation. So make some noise. There are some, things here that you can press. Yeah. Ravi, if you have a question, you can just ask. It's like, if you just want to say, then yeah. Okay. So I'm not sure if Ravi wants to ask a question or not. We'll stop the recording. We'll let the question be out of the recording then. Thank you, Matthew. Don't go away. We're not done yet.